Imagine a locomotive where the tracks are being laid down just inches ahead of the wheels. There are no brakes, no reverse gear, and no way to look at a map. You either place the next piece of steel perfectly, or you derail into the void. Standard large language model generation follows this same trajectory. It is a strict left-to-right, auto-regressive process where the model predicts a single token at a time based on the sequence that came before it. This linear momentum is the system's core limitation. Because the model calculates each token sequentially, it is unable to pause for strategic look-ahead or backtrack if a reasoning path begins to fail. In complex tasks like multi-step mathematics, this lack of reflection causes a black box failure. One minor error in an early step propels the model toward a confident but entirely illogical conclusion. Unlocking advanced reasoning requires moving away from text manipulation. We must instead impose formalized cognitive architectures that govern how the model processes information. This progression begins with establishing domain boundaries to limit the model's vast search space. Once bounded, we can structure linear thought chains, execute interactive environmental loops, and finally deploy combinatorial search trees to explore multiple solutions at once. Understanding these structures, from simple prompts to programmatic compilation, marks the transition from basic usage to high-level AI engineering. Cognitive architecture starts by restricting the model's nearly infinite latent space. Without specific constraints, the model samples from a global distribution of text that may be irrelevant to the task. Role prompting establishes these boundaries by assigning a specific persona, such as a senior data scientist, which acts as a filter for the model's outputs. Narrowing these contextual parameters shifts the model's probabilistic focus. It prioritizes the specific vocabulary and logical structures most prevalent within that expert domain, approximating the mental shortcuts humans use to navigate specialized tasks. However, relying solely on persona introduces a specific vulnerability: psychological confidence framing. Explicitly commanding a model to answer with absolute certainty actively alters its underlying cognitive approach. This framing can inadvertently weaponize alignment guardrails, as the model prioritizes fulfilling the mandate for confidence over its internal safety and accuracy checks. When forced to project absolute certainty, models have been shown to prematurely abandon step-by-step logical deduction in favor of a direct, assertive answer. This results in authoritative-sounding hallucinations, where the model provides a wrong answer with the tone of an absolute expert. While bounding identity sets the tone, it cannot replace a framework that enforces rigorous internal logic. To solve for logical consistency, we must break the direct path between input and output using a linear thought chain. The chain of thought framework inserts intermediate reasoning steps, labeled here as Z-nodes, to bridge the gap between the question and the final answer. These Z-nodes allocate explicit computation to individual steps, forcing the model to process each part before committing. Yet this remains a black box. If the model hallucinates a fact in node Z1, that error propagates through the entire chain without any mechanism to verify the data against the real world. The React framework addresses this by grounding the reasoning process in an external environment. React interleaves internal reasoning with external interactions, creating a synergistic loop of thought and action. The thought node formulates a high-level plan based on the model's current understanding of the task. The action node then executes a command, such as a Wikipedia search, to gather specific evidence from outside its pre-trained weights. Finally, the observation node intakes that factual data, bringing external reality back into the model's context window. This feedback loop allows the model to adjust its plan dynamically, halting the propagation of errors by checking its reasoning against verifiable facts. While React grounds the model, its trajectory is still linear. It cannot simultaneously explore multiple competing hypotheses. Complex planning requires a framework that enables deliberate, global decision-making across several potential paths. The tree of thoughts architecture fulfills this by converting text generation into a search problem. In this model, every reasoning step becomes a node in a combinatorial problem space. The first mechanism is the thought generator, which requires the model to propose multiple, diverse next steps from its current state. These candidates then undergo a state evaluation. The system utilizes the language model itself as a heuristic function, grading its own partial solutions before proceeding. Each branch is assigned a specific status: sure, maybe, or impossible. Impossible branches are immediately pruned, terminating reasoning paths that show no promise of reaching the goal. Algorithms like breadth-first or depth-first search then allow the model to backtrack and explore alternative maybe branches when a path hits a dead end. In the game of 24 Task, a benchmark for strategic planning, standard chain of thought prompting achieves only a 4% success rate. By utilizing this look-ahead and backtracking, Tree of Thoughts increases that success rate to 74%. This framework instantiates System 2 deliberate reasoning within a system designed for System 1 associative prediction. Manually designing these action loops and search trees for every new task is a major bottleneck for large-scale applications. The solution is the shift towards structured prompting. Frameworks like DSPY and Promptomatics function as compilers, treating prompt design as a mathematical optimization problem rather than a linguistic one. This architecture illustrates the complete automated optimization pipeline. The configuration block automatically extracts the user's intent and generates the necessary synthetic training data, bypassing manual dataset creation. The optimization engine then uses a teacher model to determine the most effective cognitive architecture for the specific task. The system chooses between chain of thought or React modules based entirely on the mathematical complexity of the input description. Optimization is guided by a cost-aware objective function that measures performance against resource usage. This formula ensures that the reasoning performance of the prompt is systematically balanced against the exponential computational cost of longer structures. Enterprise-scale prompt engineering functions as a programmatic compilation process, optimized through these automated feedback loops. This structural evolution has moved us from the vulnerable single prompt to expansive search trees and automated compilation pipelines. These models serve as execution engines capable of traversing complex, computationally optimized reasoning topologies. They are no longer just text predictors. They are platforms for high-level cognitive frameworks. The modern prompt engineer functions as a software engineer, designing the specific architectures that govern how an AI processes logic. Mastering these architectural controls allows engineers to reliably extract multi-step reasoning from a system built for